What is the uncertainty of the estimated parameters for the intercept and the slope from linear regression? We're going to start from the fact that the regression parameters are linear in the input data. What this means is that for either of them, let's take the intercept as an example, there are coefficients, I'll call them psi dagger sub j, such that the estimated intercept is equal to the sum of those coefficients times the data values. I've put a hat over beta naught to indicate that this is the estimated intercept, not the true intercept, which is just beta naught without a hat. We'll learn a lot more about those coefficients psi dagger sub j later on. We'll call them projection vector or projection coefficients. In fact, we'll get into that in considerable detail, not this lesson, but in our next lesson. I think it'll be a fascinating and beautiful mathematical journey. Let's suppose the data actually do follow our model, so that x sub j is equal to some intercept plus some slope times time plus some random noise term. And we'll assume that the epsilon sub j, the noise terms, are white noise. Beta naught is the true intercept, beta 1 is the true slope. Then the estimated intercept, beta naught hat, is equal to the sum of the projection coefficients times the data values, which happens to be this, where I've simply taken the fact that beta naught is a constant, it doesn't change over time, so I can take it outside the summation sign. Same for beta 1. Well, now we've got an interesting expression for the estimated intercept parameter. We can see later that, we will see later when we get into the details of the projection coefficients, that psi dagger sub j has some very useful properties. It includes this: the sum of all those coefficients, the sum over all j values of psi dagger sub j, has to equal 1. Also, the sum over all j values of psi dagger sub j times the time sub j is equal to 0. That's when psi dagger j is the coefficient vector for the intercept parameter. Well, now let's use those useful properties. And because of them, the first two terms on our equation drop out, or at least simplify, so the estimated intercept is beta naught hat equal to beta naught, the true intercept, plus the sum over all terms of the intercept parameter vector coefficients times the noise values. However, the expected value of the noise values is 0 for all values. So the expected value of the intercept estimate is expected value of beta naught hat is equal to the true value plus the sum of a bunch of coefficients times 0, so it's equal to the true value. In other words, the expected value of the intercept estimate is the same as the true intercept. That's the definition of beta naught hat being an unbiased estimate of the intercept parameter. And that's a good thing, actually. Well, what about its uncertainty? Well, the difference from the true value when squared gives this. It's beta naught hat minus beta squared, which is the sum of all those terms squared, which you can write as a double sum over all j values and all k values of psi dagger sub j times psi dagger sub k times epsilon sub j times epsilon sub k. Now, we're going to use the fact that epsilon is white noise. So the expected value of epsilon sub j times epsilon sub k is equal to sigma squared times delta sub jk. Sigma squared is the variance of the noise process. Delta sub jk is the Kronecker delta. It's equal to 1 when j is equal to k, otherwise it's equal to 0. And because all of those terms with j not equal to k are 0, in our double sum, the only terms that survive are the terms when j is equal to k. That means that our double sum simplifies to a single sum. So the variance of the intercept estimate, which is defined in this way, is the variance of the noise times this sum of the squares of the intercept parameter coefficients. By the way, since that's the variance, the square root of it is the standard deviation of our intercept estimate. That's a very useful result. We now have derived quite simply what is the variance of our intercept estimate. We know that its mean value, its expected value, is the true intercept. Now there's a different projection vector, psi dagger sub j, for the slope parameter, but the analysis is very similar, and the analysis shows that it too is an unbiased estimate, and that its variance is given by an extremely similar formula. The variance is the variance of the noise times the sum of the squares of the coefficients used to define that parameter. And of course, that uses the other psi dagger sub j, the one for the slope. Now, the details of the quantities psi dagger sub j, whether we're talking about the coefficients for the intercept or for the slope, they depend on the times of observation, although they do not depend on the data values. There is one very interesting special case, however. When the mean time is 0, that's to say the average time is equal to 0, we have a special case that for the intercept, the psi dagger sub j values are all the same, and they're all equal to 1 over n, with n being the total number of data values. Now that means that the intercept estimate is beta naught hat is the sum of the data values divided by n. But that's just the definition of the average data value. So in this special case, when the average time is equal to 0, the estimated intercept is the average data value. Also, when the average time is 0, the variance of that quantity is the noise variance times the sum over all n values of 1 over n squared. Well, each term is 1 over n squared. There are n such terms, so they add up to 1 over n. So the variance of the intercept parameter is the variance of the noise divided by the number of data points. Now, that happens to be the same as the usual expression for the variance of an average. So in this special case, average time being 0, the estimated intercept is the usual average of the data values, and its variance is the usual variance of the average. Now, we still need to have an estimate of what's the data variance. After all, data that includes noise doesn't come with a sign that says, hello, I'm random noise plus a trend, and my variance is such and such. We need to know, at least estimate, the variance of the white noise process. What we'll do is, we'll take the residuals from our fit, we'll use them to estimate the noise values, and we'll just estimate the variance of those residuals. There will be one difference, however, from the usual way we do things. When we estimate the variance of data, we usually use this formula. We take the sum of each value's difference from average squared, and then we divide that sum by n minus 1, n being the number of data points. The reason we divide by n minus 1 instead of n is because in this sum we subtract the average, and by subtracting the average, we remove one of the degrees of freedom of the data set. Well, in linear regression, we fit a straight line model, and that has 2 degrees of freedom. So when we remove the linear fit to generate those residuals, we've removed 2 degrees of freedom, one for the slope and one for the intercept. So when we estimate the white noise variance from the residuals, we use this formula, where we take the sum of the squares of the residuals and divide that sum by n minus 2 instead of n minus 1, because we've eliminated 2 degrees of freedom. By the way, note that I didn't put r sub j minus r bar. I did not subtract r bar because the residuals already have mean value 0, so they already represent their differences from average. Okay, so the parameters have the given mean, which is equal to the true value. and the given variance given by the formulae we just derived. But what probability distribution do they follow? Well, in general, we cannot know exactly what the probability density function for those parameters is. But their deviations are the sums of random variables with given coefficients. And because of that, the central limit theorem tells us that the probability distribution is asymptotically normal. As the number of data points gets bigger and bigger, the distribution of our parameter estimates gets closer and closer to the normal distribution, but it's only true asymptotically. There's one exception. If the noise is truly independent identically distributed Gaussian, then the parameters truly follow the normal distribution. Even when truly normal, the test statistic we design to test whether or not a parameter is significantly different from zero is what did we estimate it as divided by the standard deviation of our estimate. Now, this is not a variable which follows the normal distribution because it's the ratio of a normally distributed variable, beta hat, to the square root of a chi-square distributed variable. That's what the sigma hat estimated variance or estimated standard deviation is. Well, the ratio like that follows the t distribution. In fact, it's kind of the definition of the t distribution. So our test statistic to determine whether or not our estimated parameter is significantly different from zero is a t statistic with n minus 2 degrees of freedom, because we have n data points, but we remove 2 degrees of freedom by subtracting the 2 parameters of our best fit model. Now in the next lesson, we're going to get into quite a bit more detail about least squares regression. In fact, we're going to get into the real nitty-gritty. We're going to learn why those coefficients for the parameter coefficient vector, why they're called psi dagger. Why did I put a dagger on it? In fact, we're going to get into some of the most interesting stuff of all. We're going to use a little bit of that weird notational convention that I like to use. In fact, we'll make very good use of the Einstein summation convention. I think it's a thing of mathematical beauty. I hope you enjoy it as much as I do, and I look forward to our next meeting.